This week, we're moving on to, well, moving fluids, such called fluid dynamics. If it wasn't clear from the question itself, what you have here is you have a container with a certain amount of fluid in it, in this case water, and if you punch a hole on the side of the container, that water will squirt out from that opening. So then you have movement of water. The easiest treatment for dealing with moving fluid is with Bernoulli's equation, where we make the assumption that we can chunk up the water into many small chunks of fluids, and each of these neighboring chunks, they don't rub against each other. So it's, in a sense, the assumption of no friction. We'll be dealing with friction when we get to viscosity, but right now we're treating it as no friction. And in the case of no friction, we can sort of track the movement of a particular bit of water as it moves from, say, this point 1 as it goes all the way to this point 2. With no friction, then you can have some kind of statement about how the energy remains constant. And you can see that from the Bernoulli's equation. This first term is 1/2 rho v squared, which is similar enough to 1/2 mv squared. It's actually related to your kinetic energy. Likewise, you have rho gy1, which is similar enough to your mgh. And then this pressure term here, it's related to the work because it's related to the force that presses in on the particular little bit of fluid. So really, Bernoulli's equation derives straight from the conservation of energy formula. It's just that instead of dealing with a hunk of mass, we're dealing with a little bit of volume of fluid. So that's why everything changes from mass to density. So as long as you can envision a particular piece of fluid flowing from your starting point to your ending point, so in this case, the whole thing has to be in the fluid, you can't have air gaps or whatever, then you can relate using Bernoulli's equation to find out something about one of those points. So very similar to our energy approach, we label point 1, point 2, and we organize things in a little table. We would track the velocity or speed, we would track the height, and also the pressure. At point 2, you have some speed that we're trying to find out. The height, we can define y equals 0 to be at the bottom, so this can be 0.15 meters. And the pressure, because at this point it's open to the atmosphere, out here, this is the atmosphere, so it's at P atmosphere. For point 1, we can choose point 1 sort of to be anywhere we want, but it's easiest to pick this point right underneath the piston because we know something about that point. Specifically, we know the height, that's 0.5 meters. We also know the pressure because you know that at this point, at the top of the fluid, that fluid is supporting all this atmospheric pressure on top of it, but also this hunk of metal that's part of the piston. So in terms of pressure, you have the atmospheric pressure plus the force of the piston, or the weight of the piston, mg, divided by the area of the piston. So that gives you the added pressure from the piston, giving you all the pressure that is on that particular point on the fluid. Then for speed, in this case, because the spout here is so small, you can imagine that this wide tank compared to cross-sectional area of the entire container, that your water level doesn't drop very quickly. So as a first approximation to make our life easier, we'll say that the speed at point 1 here is roughly equal to 0. We'll double check that at the end to show you how that works. And then in the next question, we'll actually treat it properly to find out how we can relate these two things. Then another thing to just keep track of is what density to use. Well, the density you would use is, as you draw this line, which we call the streamline, you can imagine this piece of fluid moving something like that. The fluid that we draw that through is water in this case. So then now we sub and solve. No big deal. PATM goes away. And so we can rearrange the solve for V2 pretty easily. Using a calculator, take the square root. And since they asked for velocity, we have to include the direction, which is to the right, because it's going to be 9 degrees to the face of the opening. At this point, if we want to verify that the initial speed is indeed 0, we look to this equation down here, which I call Bernoulli's buddy. The key here is we're basically saying, like most liquid, the fluid is not compressible. So that whatever volume loss we have coming out this way, which is related to the volume flow rate, it's going to be the same as the volume lost here. And you can see how, because the cross-sectional area is so different, and part 2 has to move a lot for part 1 to move a little bit. In numbers, we're saying that we lose just as much volume at point 1 as we do at point 2, and volume flow rate can be obtained by multiplying the velocity or the speed with the cross-sectional area. Punch in the numbers where A2 is your cross-sectional area of the spout. You find that the speed at 1 is indeed very close to 0. Of course, if you really want to be rigorous about it, you could have used this relationship and sub it back up here and then have a little more algebraically complicated thing. But we didn't have to do it this time because the number is in fact very close to 0, so we can make that assumption and make our algebraic lives a little easier. So let's move on to part B. Once the water exits the container, each piece of water you can imagine is going to follow its own projectile motion. And somehow they say that this is 1.5 meters. We already know what my initial velocity is. And they want this range, basically, where it hits. So review, projectile motion, we list out all our initial and final conditions. I'm going to again use my I and J representation, where you have, let's say, y equals 0 here and x equals 0 over here, with this being x, this being y. So then our final is some range in the I direction and 0 in the j direction. We know the initial velocity completely horizontal in the positive I, and gravity, of course, gives you a downwards acceleration and nothing else. Looking at the j hat component, we can figure out t, then subbing that into the I hat component, of course, where the acceleration is 0, we'll work out that it lands 1.81 meters away. Of course, in reality, there's going to be a little bit of air resistance, but if you did try it out for yourself, this actually comes pretty close. So overall, even though we're seeing these new types of system with moving fluid, you can see how the concepts we covered before, such as energy and projectile motion, still applies to these more complicated systems.